Today we are going to be discussing nuclear reactors. They are efficient at producing energy in mass quantities. They make up 15% of the world's energy production, 19% of the USA's production. However, they make up 97% of France's energy production. A nuclear reactor consists of basic components, such as the fuel component, and 2 to 3 control rods. These control rods regulate the neutrons within the fuel cell. You'll see why here in a minute. It also consists of a moderator and a coolant, which is they are both usually water. And it's all in a shell, like a nice, strong, protective shell. Inside this fuel cell, usually, is uranium-235. And when we talk about nuclear reactors, we are usually talking about fission nuclear reactors, because fusion is a different process and produces far more energy than fission does, and there hasn't been a way developed yet to control it. So what happens in fission in a nuclear reactor is the uranium, gets bombarded with neutrons. And when it gets hit with these neutrons, they break up into more neutrons. Tons and tons of neutrons. Energy, that's where your energy comes from. Heat, and other elements. And in reactors, there's a self-sustaining chain reaction, which what that means is that the neutrons that broke apart from this first uranium come in and they bombard this other uranium, and it breaks up into other neutrons, and so on and so forth. Neutrons, energy, heat, and other elements. Now, these other elements are usually things like neptunium-239, or strontium, cesium, CS, or barium. Now, barium, cesium, and strontium are all waste products. They remain in the reactor until it's cleaned, which is about once a year, and they remain radioactive for thousands of years. The neptunium then decays into plutonium. And plutonium is fission just the way uranium was. Other neutrons hit it and it decays into other neutrons, energy, heat, and waste. That's basically how fission works. Now, all this produces massive amounts of heat. And also tons and tons of neutrons. So inside your fuel cell, oh, that was bad, uranium-235. You have these two, they're boron or cadmium, and they absorb the neutrons. From the last thing I drew, you could see there was tons and tons of neutrons. Well, the more neutrons, the faster the reaction, and the more heat is produced, and the more likely the reactor is to melt down. So these rods are inserted and then slowly removed until the reaction meets this sort of happy medium of heat and producing energy. Now, since all the heat is produced, there is a coolant pumped in, usually water, and pumped back out. Now the water just takes away the heat and everything and produces steam. That's why you see nuclear power plants with all the steam coming out of the top. There's a very, very, very small amount of radioactive gas produced from that. It's barely anything to worry about. The water also acts as a moderator, and what the moderator does is slows down all those neutrons and everything by just giving them something they'd have to pass through rather than just air. And when the neutrons are split apart from the uranium, they are traveling at thousands of kilometers per second, and the water slows them down to a few kilometers per second. So, yeah, that's pretty much it. That's basically how a nuclear fission reactor works. Fusion, the reason why that doesn't work is, let's say your uranium was bombarded with a neutron. Well, that neutron would stick there, and that produces so much more energy, and it's just nothing water can cool down or moderate. So really, they'd have to come up with a better protective shell and a better coolant and moderator. It's just complicated. So that's how a fission reactor works.
I bet that all that was confusing, right? Well, there's more. As you've seen, nuclear reactors are just big nuclear reactions. And as we all know, nuclear reactions have equations. The decay that was mentioned before is radioactive decay, and there are 3 types. You have alpha emission. Alpha emission is when alpha particles get taken out of a nucleus of an element, like seen here with radon going into polonium and helium. The little alpha particles at the bottom taken out of radon and split between the polonium and the helium. And that's how the equation for alpha particles work. Then you have beta emission. This is when there is a removal of electrons. And it's normally done by a little 0 over a -1e, such as the beta emission of iodine, going into xenon and taking away 1 electron. You can see at the bottom, the numbers all match up, and that's how its equation is. While gamma emission normally occurs with beta and or alpha, so it is not shown with a general equation. Now, like my friend said, nuclear reactors go through fission, a nuclear reaction in itself, which has its own general equation. And that is when uranium-235 gets hit, like she said, with a neutron, which is shown as 1 over little 0 n, it goes into and creates barium, krypton, and more neutrons. Therefore, that's why it's a fission reaction. Now, uranium-235 is actually an isotope of uranium. Uranium-238 is the more common one, but because when it is going through the same process as uranium-235, it doesn't produce the extra neutrons like uranium-235 does when it goes through fission. And then, I bet you're wondering about the whole waste and why it takes so long for them to stop being radioactive. Well, fission produces waste elements. Like we said before, there was barium, strontium, and the last one. And those 3 have half-lives. And half-life is the amount of time it takes for half a radioactive substance to disappear. So basically say that uranium-235 undergoes fission. And those will be shown by, let's say, little lines. And so uranium is 1 line, and it goes into barium, which is another line, plus strontium, which is another line. And then you'll cut those lines in half. And the time it takes to cut barium in half could be longer than the time it takes it cut strontium in half. Say barium is 10,000 years before even half of it is gone. But for strontium, it's only 1,000 years. So that's why its waste lasts longer, but it's also contained, unlike fossil fuels. It doesn't go out into the air. So, in conclusion, nuclear reactors are a very efficient source of energy. They do not produce all that pollutants that go through our air like fossil fuels do, solid and or gaseous, and they are very cheaply made with the fuel they have because uranium is a naturally reoccurring substance in the earth and can create the plutonium also needed for fission. So there you go, and that's nuclear reactors.